Uh, all right. Continuing our study of compound propositions, we will now look at the last logical operator, which is implies. This is a very common operator in mathematics. We see it everywhere. It's very important that you understand it properly. So let's get implies. The symbol for this is a little weird, but the symbol in logic for implies is a single arrow, but in math, the symbol that is used is a double arrow. But we will stick to the logic symbol, at least for this chapter. And so P implies Q means, again, as I said, P implies Q. Or equivalently, this is also very frequently written as if P, then Q. They mean exactly the same thing in logic. Now, this very important point here. When we are doing or and, both P and Q have the same role, but in implies, the P and the Q have different properties. So here, P is called the hypothesis, and Q is called the conclusion. So similarly, in if P, then Q, Q is the conclusion and P is the hypothesis. Okay, and so that's what this symbol means in English. But now this is why we delayed the study of implies till a separate chapter, because its truth table is slightly non-intuitive, and it goes as follows. P implies Q is true if either both P and Q are true. So either the hypothesis and the conclusion are both true, or, and this is the weird part, P is false. So an implication becomes true if the hypothesis is false. That's just how it is. It might feel weird, but that's what we have in logic and hence in mathematics. And all of mathematics uses this convention. So you have to stick to this. And let's see what this means. Let's build a truth table based on this information. So we have P, Q, and P implies Q. So we are building a truth table for P implies Q. For P, we'll have true, true, false, false. For Q, you have true, false, true, false. Now, if both P and Q are true, this is the first condition here. And so we will get true. P is false is the second condition, which happens here and here. So irrespective of what Q is doing, because P is false, this whole thing becomes true. And finally, we get the only time P implies Q is false is here. So the only time when P implies Q is false is when P is true, but Q is false. That is, the hypothesis is true, but the conclusion is false. That's just how it is. It will take some time to get used to this fact, but you will need to use this in all your problems. Okay, so that is implication. As far as logic is concerned, it's just another operator. So everything you could do with and or not, you can do with implies. So for example, let's do a quick problem. Determine the truth value of P implies Q implies, let's do not R, given that as before, P is true, Q is false, and R is true. So remember that we just treat this as if it were arithmetic. So we start from the innermost bracket and then move outward. So I'll just quickly do the solution. So we have P implies Q implies not R. I'll first replace PQR with the corresponding truth values. So P is true and R is true and Q is false. This is then, now we have true implies false. So let me start with the first bracket here. True implies false is false. So I will get false implies not true. Then we have a not true here, so let's get rid of that. Not true will become false. So I'll get false implies false. And because of the way implies works, false implies false is true. And so we get that the truth value of P implies Q implies not R is in fact true. So that's how you solve problems, just like you would have done with and, or, and not. The next thing I want to talk about is, before I move on from implies, let me give you one reason why this is slightly non-trivial. So example. So let us consider this statement. If x is even, then x squared is even. Here, x is a natural number. Now, I hope we agree that this is a true statement. If something is even, then its square is also even. But now let's look at what happens for particular x's. So this is true. Now, if I try this for x equals 2, then I get if 2 is even, then 4 is even. Here, this is the hypothesis. My color coding wrong. This is the hypothesis, and this is the conclusion. And the hypothesis is true, and so is the conclusion. And so this whole statement, and so this whole thing is in fact true. Now let's see what happens when x is odd. We get if 3 is even, then 9 is even. Now this might sound weird, but here's what's happening. In this case, the hypothesis itself is false. And so because the hypothesis is false, it doesn't matter what the conclusion is saying, the whole thing becomes true. And this justifies why the statement, if x is true, then x squared is true. Sorry, if x is even, then x squared is true for all x, no matter what x is, whether it's even or odd. So this is how implication shows up in mathematics. And you need to be careful of the fact that if the hypothesis is false, then it's true. It doesn't matter what the conclusion is. All right, so that is something about implication. Then we have a closely related operator to implication called by equivalence. This is not a separate operator. It can be rewritten in using implies, but I'll give it separately for now because for now, yeah, let's keep it separate. And here the symbol is two-sided arrow. Again, this is a weird thing. In math, the usual symbol for this is a double arrow, a thicker arrow. All right, and the way we read this is P double arrow Q means P if and only if Q. Or equivalently, this is actually more common. P is a necessary and sufficient condition for Q. So they both mean exactly the same thing, and they are written in logic as P double arrow Q. So that's by equivalence. And here the truth table is nicer. So P, Q is true if either both P and Q are true, or both P and Q are false. So that's why it's called by equivalence. And if I were to write a truth table, it will look like P, Q. P, if and only if Q, then we have true, true, true. All right, then the only time we get true is when they're both true or they're both false. So we get true here and true here, and we get false here and false here. So that's the truth table for P if and only if Q, or by equivalence. This is also very frequently used in math. It's mostly used for stating theorems. You will often see a theorem that says something if and only if something else. And finally, I want to say something that that we'll look at in the next video, but I just want to mention the words here, and those are contrapositive, inverse, and converse. All right, so what are contrapositive, inverse, and converse? So given a proposition P implies Q, so they are only defined for this particular kind of proposition, i.e. P implies Q. The contrapositive is not Q implies not P. The inverse is not P implies not Q. And the converse is Q implies P. So this is a bit confusing. So let me explain how to remember this. Firstly, inverse is very rarely used. So I'll just say this is rarely used. No need to memorize. Okay, so let's get inverse out of the way. So now we'll focus on the contrapositive and the converse. So let's start with the converse because it's slightly easier to remember. So how to remember the converse? So the converse is obtained by flipping the hypothesis and the conclusion. That is, if you have a statement P implies Q to start with, then to form the converse, you would just swap Q and P. And the contrapositive is flipping and negating the hypothesis and the conclusion. So P implies Q. If I were to find the contrapositive, it becomes not Q implies not P. And the inverse is not very relevant. Okay, now what is the deal with contrapositive and converse? We will see this in logical equivalence, but let me just say it in words. We will show that contrapositive is actually equivalent to the original statement. So it turns out that these two are the same. But the converse is not the same as the original statement. So P implies Q is not the same as Q implies P. And it is a logical fallacy that is very common in making arguments when we confuse a statement with its converse. And that's coming up next. But the definitions only require logical operators, implies and not. And so we stated here. Right? That's all there is to implies.